Greetings, my name is Edor Gabriel Poesina. I'm a second-year PhD student at the University of Bucharest, Romania, under the supervision of Professor Dr. Radu Tudorionescu. In this video, I'm going to present our research, a novel cartography-based curriculum learning method applied on RoNLI, the first Romanian natural language inference corpus, which was authored by myself, the esteemed Professor Dr. Cornelia Caragia from University of Illinois, Chicago, United States, and the esteemed Professor Dr. Radu Tudorionescu from University of Bucharest, Romania. During my presentation, we have 4 chapters: an introduction of the paper, the dataset, the collection methodology, and a few statistical results related to it, the models that we have employed, and the benchmark results. Our contribution is threefold. We introduced the first Romanian natural language inference corpus. We also conduct a series of experiments with async predictors on the natural language inference task. And we introduced a new curriculum learning strategy based on data cartography. The natural language inference task requires us to identify the relationship between two texts which are called the premise and the hypothesis. To collect such text, we have employed distant learning on the Romanian Wikipedia to collect approximately 64,000 data pairs. By following the work of Sadat et al., we identified 4 categories of sentence pairs which are contrastive, entailment, causal, and neutral. To further enhance our dataset, we have employed multiple individuals to obtain manual annotations over the validation and the test set, consisting of 3 k-pairs each. In order to apply distant learning, we had to identify a set of structures which accurately reflect the relationship between adjacent sentences. For example, we identified the following structures: in contrast, which reflects a contrastive sentence, in other terms, an entailment, and thus a reasoning. After searching for these structures across our text, we select the sentences that contain them as hypotheses for our datasets, and the sentences that were before them are selected as premise. In order to force the natural language models to not learn by heart the structures that we have used for search, we remove them from the hypothesis and keep just the original premise and the hypothesis with the removed structure. In order to find neutral sentences, we randomly sample across the dataset. We provide an aggregation of the dataset statistics, and we observe that we have approximately 58,000 trained samples, 3,000 validation, and 3,000 tests. We also analyze the average number of words in both the premise and the hypothesis, and the overlap ratio of the words in each of them. A few examples of the datasets. So we observed that we had the premise: under the shadow of her mother-in-law, Ulrica was never happy, or at least her life at court was not happy. And the hypothesis that we have extracted was: it was said that her private life of the king and her children was a very happy one. Over here, the structure that we identified was in contrast. It was said that her private life. So we have removed the structure in contrast and obtained this finalized sentence. And this is applied in order to extract all of the categories that we have. Another technique which we have used is data cartography, which analyzes the variability and confidence of predictions during the training phase. Data is then split into 3 categories: easy to learn, ambiguous, and hard to learn. The easy to learn is the data with the 33% highest confidence. Ambiguous are the data with the 33% data with highest variability, while the hard to learn data are the 33% with the lowest confidence. This means that some of the data splits could have overlaps between them. We present a few statistics about the data difficulty splits that were obtained through data cartography. It's interesting to note the fact that there are virtually no data points from both contrastive and entailment in the easy to learn set. We also report the Fleiss kappa coefficient for the annotations provided by the manual annotators. It validates the previous data cartography technique, the fact that the easy to learn is the one that has the highest Fleiss kappa correlation, followed by ambiguous and hard to learn, showing that even the annotators had a more difficult time to annotate data in one of the latter splits. We conducted experiments with 18 different models. 2 are based on shallow classifiers, 2 large language models, 2 versions of multilingual BERT, and 12 versions of Romanian BERT. In terms of the shallow models, we have applied the continuous bag of words for each of the sentences and averaged the embeddings of the words to obtain an embedding for each of the sentence. We have concatenated these embeddings and put them through either a support vector machine or a softmax classification or a prediction head. We have employed 2 large language models, which are RoGPT2, which is fine-tuned on our task, and a zero-shot large language model, which is GPT 3.5. In terms of the BERT models that we have tried out, we used a zero-shot multilingual BERT model, a fine-tuned BERT model for the natural language inference task, a Romanian BERT, which was trained on Romanian data, and we've also fine-tuned this Romanian BERT on spurious correlations, meaning that we only fed to it the hypothesis in order to see if the pair of data is actually very simplistic and the relationship can just be observed by looking at one of the sentences. After which we have used RoBERT in conjunction with data cartography by fine-tuning on different difficulty splits. We have employed a curriculum learning with a text length as a difficulty metric, and we have employed a curriculum learning using a semantic text similarity as difficulty metric. We propose a curriculum learning based on the difficult subset generated with data cartography. We fine-tune our RoBERT models in the following way. We take the total number of training steps that we had usually used for fine-tuning a RoBERT model and split it in 3 stages. In the first stage, which is 25% of the training steps, we fine-tune only on the easy-to-learn data. In the second stage, which is also 25%, we add to this data the ambiguous split that the data cartography has given us. In the third stage, which is 50% of the training time, we then fine-tune on all of the remaining data. To address one of the drawbacks that the data cartography data splits introduced, we defined a custom difficulty metric as follows. Previously, the easy-to-learn and hard-to-learn categories focused only on confidence, while the ambiguous focused only on variability. In our difficulty metric, we take into account both the confidence and variability when giving out a score to a certain data point. We use it as following. The upper left corner are considered points that are easy because they have both high confidence and low variability. Going to the middle right section where data points with a medium difficulty can be found. The hardest difficulty points are the one in the lower left corner because they have very low confidence and very low variability. Our final novel model is the one that obtains the highest score across the benchmark. We combine our custom difficulty metric with a stratified sampling approach. In one of the earlier slides, we have observed that the contrastive and entailment data points do not appear in the easy-to-learn difficulty split, meaning that the model is not exposed to it early. In our technique, by applying a stratified sampling, we make sure that we have data points from contrastive and entailment in all of the training stages. This allows the model to be exposed earlier to data and to accustom ahead of time with all of the classes. In the following table, we present the results of our techniques, where we have also applied oversampling across some of the models. We can observe that the highest performance is obtained with the stratified curriculum learning technique and the curriculum learning based on semantic text similarity. In order to also validate our results across multiple datasets, we have also employed the best 2 performing models on the RoNLI dataset, which has the same classes, and we have obtained that the stratified curriculum learning technique has a higher score than the baseline presented in the original paper. Please feel free to check out the dataset and the code for it at the following QR code and URL, and also feel free to drop in a message at any of the 2 following emails attached. Thank you very much.